Okay, so this is the next topic that we're doing, trigonometry. The first thing that you need to know about this is reciprocal trigonometric functions. So in paper one, you've done sine, cos, tan. Now we've got three new functions: cosecant, secant, and cot. Cosecant is 1 over sine, secant is 1 over cos, cot is 1 over tan. Now, the way to remember these is sometimes cosecant and secant, they get mixed up. Look at third letters. Third letter for cosecant is S. That's the reciprocal of sine. Third letter for secant is C. That's the reciprocal of cos. Third letter of cot is T. That's the reciprocal of tan. That's one way that you can use to remember this in case you end up mixing them up sometimes. So these are three new functions that we've got. These are called reciprocal functions. Now, you need to be able to solve equations involving these functions. For example, if you have secant theta equal to, how would you solve this equation? Now, your calculator does not have a secant, cosecant, or cot button. So when you have reciprocal functions in an equation, you have to convert them to the base function. So secant can be written as 1 over cos, and that becomes cos theta equals 1 over 2. You find the basic angle, look at quadrants, and write down the answers based on that. Okay. In paper one, you had done these two identities: sine square theta plus cos square theta is identical to 1. 1 plus tan square theta is identical to secant square theta. Using these identities, we could just rearrange them and get sine square identical to 1 over cos square identical to 1 minus sine square. So you could convert sine square to cos square to sine square. Similarly, you had, this was the only one that you done. Was paper one, the other one. Okay, these two are the ones that you're done in paper one: sine square theta plus cos square theta equals 1, and tan theta equals sine theta over cos theta. These were two identities that you're done in paper one. Now, you could convert sine square to cos square or cos square to sine square using this. And using this other identity, you could say when you have sine over cos, that could be written as tan theta. Now, here we have some new identities. First of all, tan theta is sine over cos. We could take reciprocal on both sides to make it cot theta equal to cos theta over sine theta. We will be using this identity a lot of times, and it's not given in the formula sheet, so it helps to remember this. It's just the reciprocal of this. If tan is sine over cos, then cot is cos over sine. Okay, this is not given in the formula sheet, but we'll be using this a lot, so keep this in mind. But then you have two new identities which come from the reciprocal trigonometric functions. 1 plus tan square is secant square, 1 plus cot square is cosecant square. Now, using these identities, what you can do is you can convert tan square to secant square if you want, secant square to tan square. Similarly, you can convert cot square to secant square, cot square to secant square, cot square to cosecant square, and cosecant square to cot square. You can do these conversions using these identities. Okay. Now, even if you don't memorize these identities, the least that you need to remember is that tan square and secant square, they have some identity between them. Otherwise, you will not get ideas in the exam, how to solve equations or how to prove identities. The minimum that you need to remember is that tan square can be converted to secant square and secant square can be converted to tan square. And then for the exact identity, you can look at the formula sheet. But at least this much you need to remember. Similarly, that cot square and cosecant square, they are related to each other. One can be converted to the other. You should memorize that, at least that much, okay? Now, let's say you have an equation like this. How do you solve any trigonometric equation? You want only one type of function, sine, cos, tan, and only one type of angle. In this case, we've got secant square, and this is tan. How do we convert them to one function? We could say secant square can be written as 1 plus tan square. And then we simplify that. That gives us a quadratic equation in terms of tan. We solve the quadratic, find the basic angle, write down the final answers based on that. The interval that we were given in this case was from 0 to 2 pi. We got the basic angle for both of them. As in, we first of all got two values of tan theta, this and this. We find the basic angle, looked at the quadrants, and wrote down the answers based on that. Okay. So that's what you may have to do. Then we have some more identities. So first of all, we've got compound angle identities. Now, what are compound angles? Let's say you have an equation that looks like this. Sine of theta plus 60 plus cos theta equals 0. How do you solve this equation? These are two different angles. This is another angle, this is another angle. Using the earlier methods, we could not solve these equations. We have to expand this thing somehow. Now, this angle, theta plus 60, when you have two angles, two numbers or two expressions being added or subtracted, we call this a compound angle. We have identities for expanding them, and it's not this. Sine theta plus 60 is not the same as sine theta plus sine 60. That's not correct. We expand it using some identities, and they look like this. We have 6 identities, 2 for sine, 2 for cos, 2 for tan. Sine A plus B is sine A cos B plus cos A sine B. Sine A minus B is sine A cos B minus cos A sine B. Similarly, for cos and tan, you can look at these identities. Whenever you have these compound angles, we can expand them using these identities. All of them are given in the formula sheet, although they're written in a relatively more concise way. I'll show them how exactly. But using these identities now, what you can do is, for example, in this case, you had sine theta plus 60. You could expand sine theta plus 60 like this, sine theta into cos 60 plus cos theta into sine 60. And then cos 60 becomes 1 over 2, sine 60 is under root 3 over 2. And then you could simplify that further after that to solve that equation. This is what I've done that. So we first of all applied that identity to simplify that. And then we had sine in one term, cos in another term, cos in another term. To convert it to tan, we could just divide the whole equation by cos like this, right? We divide the whole equation by cos, it converts to tan, and then you can solve that equation in terms of tan, find the basic angle, and find the result from that. Then you have some double angle identities. What are double angles? When you have 2 times something, it could be 2x, it could be 2 theta. These are called double angles, okay? For expanding double angles as well, we've got some identities. They're given in the formula sheet as well. So this topic is more about application, as in these identities are all given in the formula sheet. We need to be able to use them. That's why we'll have a look at a number of examples. Sine 2a, that's 2 sine a cos a. Cos 2a is cos square a minus sine square a. 2 cos square a minus 1, 1 minus 2 sine square a. There are 3 different forms that we have for this. We can use any of them generally. If we know we have to convert something to cos, then we can use this one. If we know that we want sine in the final result, then we can use this. If we are not sure, then you can use any of them. It doesn't matter. But we have these 3 different forms. They're just coming from these identities that sine square is 1 minus cos square is 1 minus sine square. So from that, we can actually get these 3 different forms. Then you have a double angle identity for tan. That's 2 tan a divided by 1 minus tan square a. We've got these double angle identities. We can use these to expand these expressions. Expanding means we want to convert it to just angle x, this just angle theta. We want to get rid of that 2 times that. Okay, that's what it means to expand these expressions. These are double angle identities. Now you can use them, for example, to solve equations like these. Sine 2x minus cos x equals 0. How do you do that? Apply the double angle identity for sine, it becomes 2 sine x cos x minus cos x equals 0. And now if you take cos x common, that gives you 2 equations, cos x equals 0, 2 sine x minus 1 equals 0. You've got this interval given, solve these equations further, find the basic angle, use quadrants, and find the values of x that you get from them, right? This is how these identities are given in the formula sheet, right? So these are all the identities that are given in the formula sheet that I've showed you before. This one is not given, so you can remember that you just take reciprocal of this tan identity, and that will give you this. The compound angle identities that are written in a concise way like this. These are 2 identities in one single row. For example, for cos, you have plus written above here, minus written above here. So you can say the plus on the left side corresponds to minus on the right side. Similarly, if you have minus on the left side, then you have plus on the right side. For tan, for instance, this is tan of A plus B. That is identical to tan A plus tan B divided by 1 minus tan A tan B, right? So the sign that is written above, that corresponds to the sign that's written above on the other side as well. The sign that's written below, that corresponds to the sign that's written below on the other side as well. So tan A minus B, that is tan A minus tan B divided by 1 plus tan A tan B. And that's the result and that's the identity that you've got. So these are 6 identities written in 3 different lines like this. Then you've got these double angle identities. Cos 2a, it has 3 different forms. Sin 2a is only one form, and tan 2a. Okay. This is how these identities are given. Now, using these identities, you should be able to expand some other expressions as well. For example, what if you had sine of 4 theta? How would you expand that? Sine of 4 theta. You could expand sine of 4 theta like this. You could say sine 4 theta is the same thing as saying sine of 2 theta plus 2 theta. You could write that as a compound angle, right? Sine of 2 theta plus 2 theta. And then apply the compound angle identity for sine a cos b plus cos a sin b, and then simplify that, you end up getting this expression. And depending on what you want afterwards, you can convert it to that form, but that's what you get after simplification of this. You apply the double angle identity for this, double angle identity for this, simplify everything, and that gives you some result. Okay. An alternative for this could be using the double angle identity for sine of 4 theta. You could also do this. Since you have the double angle identity for sine, that's sine of 2a, that is identical to 2 sine a into cos of a. We could say whatever is the angle on the left side here, on the right side, the angle is half of that. So if we had 4 theta on the left side, on the right side, it would just be 2 theta and 2 theta, right? So we could do it directly like this as well, and then simplify it further, expand sine 2 theta, expand cos of 2 theta, and then that would give you the simplified form after that. Okay, so that's how you expand sine of 4 theta. Similarly for cos 4 theta and tan 4 theta as well, you can either use the double angle identity or the compound angle identity. Now, compound angle means 2 theta plus 2 theta in this case. Double angle, whatever is the angle on the left side and the right, it has to be half of that. So in this case, if the angle is 4 theta on the right side, it will be 2 theta and 2 theta. Right? It's the same for cos and tan as well, as in it works similarly to this. If you have 3 theta, in this case, you can't use double angle. You can only use compound angle. 3 theta, sine of 3 theta, cos of 3 theta, tan of 3 theta. This can be expanded using the compound angle identity. We'll say this is cos of 2 theta plus theta, right? Apply the identity for this. That will become cos 2 theta into cos theta minus sine 2 theta into sine theta. And then you simplify this further, apply the double angle identity for this, apply the double angle identity for this, and then that will simplify further to give you something like this. Now, depending on what you want at the end, you can convert it to either only sine or only cos. That would depend on the question, but that's the general method that would have to be applied when you have 3 times theta. Now, the double angle identities that we saw earlier, we could also come up with half angle identities from that. Now, what does that mean? If you have sine of 2a, that is 2 sine a cos a. We could also make an identity like this from that. That if the angle on the left side was theta, let's say it was sine theta, then on the right side, it should be half of that. So what's half of theta? That's half theta. So this identity, we could also say, this also tells us that sine of theta, that can be written as 2 sine of half theta into cos of half theta, right? So that's something that you'll have to do in some more complicated problems as well. Similarly, for cos 2a, we know that cos 2a is cos square a minus sine square a, right? We could say cos of theta, that could be cos square half theta minus sine square half theta. We could use this identity like this as well here. Okay. For example, this is an actual question. If I remember correctly, if you have sine theta minus 2 cos half theta equal to 0, and you want to solve this equation, how do you do that? You've got half theta angle here. One way to do this could be that since you want the same angle, right? For solving any equation, we want the same type of angle. Now, this is theta, this is half theta. So we either have to convert this half theta to theta, which is more complicated, or we convert theta to half theta. So that's what we do. We can say sine theta, using this double angle identity, we could write sine theta as 2 sine of half theta into cos of half theta. So it's written like this. And then you take cos half theta, 2 cos half theta common there. You get this equation, you get another equation, you solve these two separately, and you get the result from that. An alternative, relatively easier one, easier way of solving this could be to use a substitution in the very beginning, like this, that you say, let A equals some other letter, right? Let A equals half theta. If you were to do that in the very beginning, then this equation could actually be written like this. In this particular example, we could say, let's use a substitution A equals half theta, and then we could write this as sine of 2A minus 2 cos A equal to 0. And then we could solve this equation in terms of A. At the end, put that substitution back. Put A equal to half theta, put half theta in place of A, and then find the values of theta from that. But when we do that, remember, we have to adjust the interval as well. For example, if the interval for theta, let's say that was given to be from 0 to pi, then the interval 0 to 2 pi, let's say, then the interval that we would have for A would be 0 to pi. Right? We learned this in paper 1, that we use a substitution. When we use a substitution, the interval gets changed as well. When we put 0 here, the lower limit will be 0. When we have 2 pi here, the upper limit becomes pi there. Okay. All right. So that's what you can do in some cases as well. You can use half angle identities like this, right? Similarly, as we will see later in integration, you can also use. Let me show that to you here as well. We will see this later. For example, for integrating sine squared theta, we have to use the double angle identity for that as well. How would we do that? We have this identity cos 2a, that is equal to 1 minus 2 sine square a. And then if we make sine square a the subject from this, that gives us 1 minus cos 2a divided by 2. And we make the sine square a the subject. Now, using this, we could say that sine square theta could be written as 1 minus cos 2 theta divided by 2. So in integration, we have to do this a lot. For integrating even powers of sine and cos, this is the identity that we use, the double angle identity for cos, like this, right? So we will be looking at this later on again in integration as well when we do that. Okay, let's move on. Then you have to prove identities, right? So just like in paper 1, you will have some identities. You'll have some identities that you would have to prove. For example, you have this identity. Now, how do we prove identities? We've done this in paper 1 as well. But in this case, you'll have more complicated identities. First of all, which side do you start from? Now, the way these are going to be formulated in your exam would be that the left side would almost always be more complex. So that is what you would start. That is where you would start from. So generally, they will write the identities like this, that you would start from the left side and equate that to the right side. However, you should still, uh, think about which side is going to be more efficient to start, because it can happen that starting from the right side in some rare case might be a better idea. So how do you decide which side to start from? You start from the more complex side. Now, how do you decide which side is more complex? The side that has compound angles, the side that has compound or double angles, we say that is more complex. So this will be the order of priority. We start from the first rule, compound and double angle. If we can differentiate based on that, just do that. So in this case, for example, the left side, it has double angles like this, right? So that is more complex. Even though the right side has power, that's not what introduces complexity. It's the multiple. If it's multiplying by something, or if something is being added or subtracted inside the angle, that is what makes the expression more complex. On the left side, you have double angles here. You can say that is more complex. So this is one thing that you need to decide on whether to start from the left side or left hand side or the right hand side. The second is different types of functions. If none of the sides has compound or double angles, you start from the side that has more different functions. For example, if one side has sine and cos and the other side only has tan, then you start from the side that has sine and cos, right? And then if one side has fraction and the other does not have fraction, you start from the side that has fraction, because it's easier to convert fraction to a non-fraction as compared to the other way around. And if none of them help you differentiate between the two sides, then you see whichever side has more number of terms. So if one side has 3 terms and the other side only has 1 term, then converting 3 to 1 is easier as compared to the other way around. But mostly you'll be able to decide based on the first 2 in paper 3. Compound double angles, you start from that. Otherwise, the side that has more different types of functions, you start from that. In most cases, you will be starting from the left-hand side. They write them like this. However, you can work either way. You can start from the left-hand side, equate that equal to the right-hand side. You can start from the right-hand side, equate that equal to the left-hand side. Or this is also possible that you simplify both sides and separately. Simplify the left-hand side as well, simplify the right-hand side as well, and then you meet somewhere in the middle. This is something that we will be doing in some more complicated identities, in which on both sides we have double or compound angles. For example, on the left side, you might have, for instance, sine of 2 theta plus something. Let's say 2 theta plus pi over 3. On the right side, you might have cos of 3 theta, right? Let's suppose both sides have these compound angles. Now, what do you do in that case? In this case, when you have compound or double angles on both sides, it's a good idea to simplify both sides, right? That will make this simpler. You simplify both sides, and then somewhere in the middle, when both of them are equal to each other, you say the identity is proved. However, when you do that, you do not take terms from one side to the other. That is not allowed. While you are proving identities, you're not allowed to take a term from one side to the other, because that will be assuming that the identity is true. But you have to prove that the identity is true. So while you're proving identities, you are not supposed to take terms from one side to the other. So if you're using this method, then you keep them separate. Keep the left-hand side separate, the right-hand side separate, and try to meet somewhere in the middle as you go along, where they become equal to each other. Now, these are not any standard rules, but some tips that you learn when you practice a lot, and they help you prove identities a bit more efficiently. First of all, you would find it helpful to keep the denominators unsimplified. That means keep them in factorized form, so that if there's any cancellation that's possible in a later step, you can do that. For example, if you have sine theta into 1 plus cos theta in the denominator, it's better to keep it like this rather than simplifying it in this form, because it is possible that in a later step in the numerator, you end up getting something that you can do some cancellation on. For example, you might have 1 plus cos theta whole square in the denominator, and you might be able to cancel out 1 power of 1 plus cos theta with 1 power of 1 plus cos theta in the denominator. And that would help. If you simplify that, then it becomes difficult for you to think of factorizing that again and then doing the cancellation. Okay, so it's helpful to keep the denominator unsimplified to see if any cancellation is possible. Then these identities are used a lot. This first identity in particular, the algebraic identity, a square minus b square, that is a plus b into a minus b. You have to use that a lot while proving identities. For example, if you have 1 minus tan square theta, you could write that as 1 square minus tan square theta, and that becomes 1 plus tan theta into 1 minus tan theta, right? So this is used a lot, so keep that in mind. If you had 9 minus 9 tan square theta, for instance, you could say that's 3 squared minus 3 tan theta whole squared, and then use that identity on that, and so on, right? So a square minus b square, this identity, to factorize something, that's used a lot, which can then help you do some cancellation in the next step as well when you factorize that. When you have tan on one side, and the one that you're starting from, and there's no tan on the other side. For example, you're proving an identity. On the left side of the identity, you have tan, and that's what you're starting from. On the other side, there's no tan. Then it's more efficient to convert tan to sine over cos right away. And when you look at some examples, you'd find that this is very helpful. Convert tan to sine over cos in the very beginning rather than doing that at the end. That will simplify things for you. Okay, if you have tan, convert that to sine over cos. If you have cot, convert that to cos over sine. So work with work in sine and cos instead of tan and cot, because the identities for sine and cos, they don't have fractions in them. Tan's identities, it has fractions, so it's easier to avoid it if there's no tan on the other side. If you want tan in the final result, then of course you can keep it in that form. But if on the other side there's no tan involved, then convert it to sine over cos right away and convert cot to cos over sine right away. That will simplify things for you. If you have double angles in secant, cosecant, and cot, again, since there are no double angle identities that we have written for the reciprocal trigonometric functions, you will convert them to sine, cos, tan, their base functions. Secant 2 theta is 1 over cos 2 theta. Cosecant is 1 over sine 2 theta. Cot, you could write that as either 1 over tan 2 theta or cos 2 theta over sine 2 theta, and then simplify that further. This is an example. We have seen how to deal with this already before. We have to prove this identity. Now we start from the left-hand side. If we start from the left-hand side, we've got cos 4 theta here, right? How do you expand cos 4 theta? We know that cos 2 theta is 2 cos squared theta minus 1. What about cos 4 theta? If you want to use the double angle identity, we can say whatever is the angle on the left side, what happens on the right side is it becomes half of that. So it becomes cos of 4 theta equals 2 cos squared 2 theta minus 1. Now here it's very important to understand the notation that we've got. Sine square x is just a short way of writing sine of x whole squared. The actual function is sine of x whole squared. Sine square x is just a short form of writing that. Cos square x, again, it's this short way of writing cos of x whole squared. The actual mathematical form is this. So when you have cos square 2 theta here, what does that really mean? Cos square 2 theta basically means it's cos 2 theta whole square, right? So we have a whole square like that. And now you can expand cos 2 theta using the double angle identity for cos again. So we've applied the double angle identity once, and that gave us 2 cos squared 2 theta minus 1 here. But then we have to apply the double angle identity once more to simplify cos 2 theta, and that gives us 2 cos squared theta minus 1 inside the square here. And we simplify that further, and that gives us this for cos 4 theta. And look at the working for that. We input that here now in place of cos 4 theta, simplify everything, and that identity gets proved. Okay. Now, this is another concept that we have here, and that is that they ask you to convert something, they ask you to convert expressions to a form like this: r sine theta plus alpha, r sine theta minus alpha, r cos theta plus alpha, r cos theta minus alpha. Now, how would this work? For example, you have this expression 4 sine theta minus 3 cos theta, that's identical to r sine of theta minus alpha. Now, there's a background of this, where this comes from. You can have a look at this. We want to convert it to r sine of theta minus alpha. We can simplify the right-hand side here and simplify that. From that, we get this expression on the left side, this expression on the right side. We do comparison on both sides. We get two equations from that, and we find the values of r and alpha from that. However, from this process, we end up getting some formulas that we will be using directly. We will not be using this method. This is the logic behind the formulas that we will be using. What we'll actually do is, there are 4 different forms that are possible. That they can ask you to convert something to. They can ask you to convert something to r sine of theta plus alpha, r sine of theta minus alpha, r cos of theta minus alpha, r cos of theta plus alpha. These are the 4 different forms in which they can ask you to convert something. Now, the expression that you would have to convert to that, it would have 2 terms, one sine term and one cos term, right? One sine term and one cos term. If you want to convert to sine, the first term here has to be sine. Okay, so the first term has to be sine. So when you want to convert to sine, you can see the first term is sine here, it's being converted to sine. The first term is sine here, it's being converted to sine. When it's being converted to cos, the first term is cos here, right? When it's being converted to cos, the first term is cos here. So that's important, that the first term has to be the one to which that you want to convert it to. And then inside, It'll either be plus alpha or minus alpha. In case of the sine function, if you have plus here, you have plus here as well. If you have minus here, you've got minus here as well, because these identities come from the compound, and these formulas come from, or these forms come from the compound angle identities for sine and cos. If you remember the sine angle identity for the compound angle identity for sine, it has the same signs on both sides. So sine of a plus b, that is sine a cos b plus cos a sine b. For cos, however, the signs are different. When you have plus on the left side, you have minus on the right. When you have minus on the left side, you have plus on the right. So in these forms that you see here, in case of sine function, plus is plus, minus corresponds to minus. In case of the cos function, it's the opposite. When you have plus on the left side, you have minus here. When you have minus on the left side, you have plus here. Okay. But normally you would not have to think about the sign yourself. But this is important, that whatever is the first function, that is what you should have here that you want to convert it to. Now, once that is the case, you can use the formulas. You can use these formulas to find the values of r and alpha directly. What formulas? R is equal to square root of a squared plus b squared, and tan alpha is equal to b over a. You can use these formulas to find the values of r and alpha when you have these standard forms like this. Okay, r equals square root of a squared plus b squared. A is the coefficient of the first term here. B is the coefficient of the second term here. Just the positive values. We do not consider the sign in that. That's not required. Just these numbers, right? The coefficient outside, the magnitude of the coefficient, they are a and b. The first number is a, the second is b. Okay, and we can just use these formulas to find the values of r and alpha. For example, if you had 4 sine theta minus 3 cos theta, we wanted to convert that to r sine of theta minus alpha. All we have to do is we say a is equal to 4 and b is equal to 3. Use the formulas to find the values of r and alpha, and you get them like this. If they had 8 sine theta plus 6 cos theta, and you wanted to convert that to r cos of theta minus alpha. Now, in this case, you see, you have to be careful. They have sine here. They want you to convert it to cos. You cannot do it directly. You have to first rearrange it such that cos becomes the first term, right? So you write it as 6 cos theta plus 8 sine theta like this, okay? And now this number is a and this number is b. Now you can use the formulas, otherwise a and b will switch and the value of alpha would end up being wrong. So you have to make sure that you write cos as the first term in this case, because that's what you want to convert it to. So this number would be a, this number would be b. Use the formulas and you get that form for that. This is the result that we get. Okay, so they can, now why is that important? They can you will have to solve equations like this using this particular form. So for example, they're saying by expressing this thing in the form r sine of theta minus alpha, solve this equation. Now we cannot solve this equation directly. If we had 0 on the other side, then we could solve it. We could convert it to tan, right? By taking cos to the other side and then dividing by tan. If the number is something else, we've got 7 here. We do not know how to do that using the P1 methods that we know earlier. How do we do this? How do we solve this equation? We first of all convert the left-hand side to this form, r sine of theta minus alpha. These are two different functions, right? We want to convert them to a single function. For that, we convert it to this form. So let's do that. 8 sine theta minus 6 cos theta, that has to be converted to this form. R sine of theta minus alpha. Now the first term is the same. Yes, that is the same. So that means it is the standard form. You can find the values of r and alpha from this. And it turns out to be 10 sine of theta minus 10 sine of theta minus 36.87. So the left-hand side converts to this form. So now that equation can be written like this: 10 sine of theta minus 36.87 equals 7. And that's the result that we've got. And now, after this is just paper 1 trigonometry, we can solve it further using substitution. So whatever is inside, you substitute that with another letter. Let a equals this, and then you adjust the interval accordingly as well. When theta is 0, the value for a is minus 36.87. When theta is 360, the value for a is 323.13. And then you solve this equation in terms of A, find all the possible values of A inside this interval, and then use that, put that substitution back to find the corresponding values of theta like this. This is something that you should have done in paper one. If you do not remember this, have a look at P1 trigonometry revision video, P1 trigonometry revision video. You will find this explained in a bit more detail there. You can have a look at that P1 trigonometry revision video, okay? Yeah, so it's going to take around, I think, 15-20 more minutes. Okay, so we'll end around 12, hopefully. Why is it important to adjust the interval? Because why is it important? Because that we adjust the interval. Because the interval that's given is for theta, right? Theta is from 0 to 360. When we convert it to A, now the angle here is A. We are finding the values of A. So in order to look at the possible values of A, in order to find the possible values of A, we need to know what the minimum value of A can be and what the maximum value of A can be, because the angle is A, the angle is not theta, right? This is the angle. They gave us the interval for theta. So we have to find the corresponding interval for A, right? If we don't do that, we can sometimes end up missing a possible answer. In this case, that's not happening, but you will see in a lot of cases, you will end up missing out on a possible solution if you do not adjust the interval. So that's important, okay? If you want to understand this in detail, how this process works, P1 revision, P1 trigonometry revision video. Okay, you can have a look at that, and it's explained in a bit more detail there. So let's have a look at this. Express 4 sine theta minus 3 cos theta in this form, r sine of theta minus alpha, where r is greater than 0 and alpha is between 0 and 90 degrees. Now, the first part is straightforward. Let's say we've done that. The second part as well, it's an equation that we've got to solve. We use a substitution again, use the substitution, find the possible values of A, and in this case, you find the values of A and then find the corresponding values of theta, and you get this result. So the first two parts are relatively straightforward. Let's have a look at the last part. Sometimes they end up, sometimes they give you something like this. To find the greatest value of something, least value of something. I've seen such questions, at least one question in one of the recent papers as well. They're asking you to find the greatest possible value of this fraction. Now, how do you find that? Remember, sine and cos, both of them, they are between -1 and 1. But the problem is, we've got both of these functions. We can't input individual values for them as 1 and -1. We need to convert them to a single function, first of all. If you remember in paper one functions, to be able to find range of a function, range of a trigonometric function, we first needed to convert everything to only one type of function. This is two functions, sine and cos. So we first of all have to convert it to one function. We have done that in the first part. In the first part, what we've done is we have converted 4 sine theta minus 3 cos theta to this form, r sine of theta minus alpha. So what we can do is we can write it in that form so that it becomes 1 over 5 sine of theta minus 36.87. This thing can be replaced with 5 sine of 36.8, 5 sine of theta minus 36.87 plus 6 is outside as it is. Now, once we have it converted to this form, what's the greatest possible value for this? Now, for sine function, we know sine function is always between -1 and +1. So from this function, we consider the extreme possible values. What are the extreme possible values of sine? It's 1 and -1. So we see what happens when sine is 1, and we see what happens when sine is -1. We input 1 in place of that once, we input -1 in place of that once. When we input 1, we get a result that is 1 over 11 from that. When we input -1, we get 1 from that. Now, the smaller value is going to be the least value of this fraction. The greater value is going to be the greatest possible value of this fraction. We were looking for the greatest value, and that's 1. That's the solution that we've got for this, right? So it's similar to the range questions in paper one functions. We had to find the range of this trigonometry. We had to find the maximum possible value of this function. We look at the extreme values of sine. We input 1 in that once, we input -1 in that once, and then that gives us the result. Okay, so sometimes it can be something more complicated like this. So this is another relatively complicated example. I'll just show this to you. You can have a look at this in your own time. Then in the first part, they are just asking you to convert this expression to r cos of theta minus alpha. How do we do that? Is it the standard form? Yes, cos, it is the standard form. Use the formulas, and that gives you the values of r and alpha. In the second part, they're saying, hence, in each of the following cases, find the smallest positive angle theta which satisfies this equation and this equation. Now, how do we do that? Smallest positive angle theta. We're looking for positive angle theta. So that means theta has to be greater than 0, right? That's the condition that we've got. Theta is greater than 0. How do we solve these equations now? Now, for the first part, okay, let's explain this. For the first part, and the left side, you've already converted it to this form, 4 cos of theta minus 52.24 degrees. So you replace it with that. And now we have to solve this equation. Theta is greater than 0. How do we solve such equation? We can use a substitution. We can say let A equals theta minus 52.24 degrees, right? Now the interval that we had was for theta. Theta was greater than 0. What about A? If we input theta equal to 0 here, A is going to be greater than minus 52.4 degrees, 52.24 degrees. So when we look for the values of A, they have to be greater than minus 52.24 degrees, right? Theta was greater than 0, but A corresponding to that turns out to be this. Now from this we get cos A equals minus 1. When is cos minus 1? In this interval, well, it first happens at 180 degrees. If you think about the graph, so the graph looks like it happens at 180 degrees. That cos function reaches minus 1. So the value for A that we're getting is 180. We put that substitution back and we get that value of theta from this. Theta minus 52.24 equals 180. That gives us the value for theta. But now if you look at the next part, they have changed it slightly. They have under root 6 cos of half theta plus under root 10 sine of half theta, that equals 3. Now, instead of theta here, they have half theta. So what happens in this case? The form that we had there, in the first part, what we did was under root 6 cos theta plus under root 10 sine theta. We converted that to this form, right? Now, in this equation, instead of theta, they have half theta. So we can say, in this form, we would just replace theta with half theta. So it becomes 4 cos of half theta minus 52.24 degrees. That equals 3. This is the equation that we end up getting from this. Again, use a substitution. Let A equals half theta minus 52.24 degrees. If theta is greater than 0, find the corresponding value for A. That again turns out to be that A greater than minus 52.24 degrees. Now, it becomes cos A equals 3 over 4. We find the basic angle. The basic angle turns out to be 41.41 degrees. Now, in this case, you have to be a bit careful. The basic angle is 41.41. Cos is positive. Cos can be positive in the first quadrant or in the fourth quadrant. What do we want? What are we looking for? We were looking for the smallest positive angle theta, the smallest value in this interval when theta is greater than 0. When theta is greater than 0, A is greater than minus 52.24 degrees. That means A could be negative as well. So in the fourth quadrant, we also have to see if there's any negative value that falls in this interval. In the previous case, it did not. We had 180 degrees as the basic angle. So 180 degrees as a possible value of minus 1. On the left side, it was actually minus 180. That is outside the interval, so we did not consider that. But in this case, the basic angle is 52.24 degrees. The basic angle is 52.24 degrees. No, I'm sorry. The basic angle is 41.41 degrees. And the interval is that A is greater than minus 2.24 degrees. Now, if you look at the fourth quadrant here, this angle minus 41.41 degrees, this actually falls in this interval. So A equals 41.41 degrees. That is the smallest value of A that we have in this interval. We want the smallest value of theta in this interval, right? So that means we want the smallest value of A in this interval. The smallest value of A that we're getting is not 41.41 in the first quadrant. There's another value that's even smaller, and that's negative 41.41. That's what we use here. because we wanted the smallest value in this interval. And now we put that substitution back, half theta minus 52.24 degrees, that equals this. The value of theta that we get from that is 21.7. And that's the smallest positive value of theta that we have as the solution of this equation. Okay. Makes sense? This is quite complicated. I'll just leave it here, as in if you do not remember this concept from paper one, especially of how we have to adjust this, how we have to use the substitution, and then adjust that interval, and then find the values in that particular interval. You can have a look at this again in your own time. Let's move on. Sometimes you have to solve simultaneous equations as well. For example, you're given two equations. One is this, another is this, and they want you to find the exact value of tan of a minus b without a calculator. The calculator is not going to give you exact value for this. Tan of a minus b. Now, how do you find that? Tan of a minus b is actually the same thing as tan a minus tan b divided by 1 plus tan a tan b. So the problem is we want to find out the values of tan a and tan b, and then we can just input them in this identity and we would get the result from that. How do we do that? We've got these two equations. Sine of a plus 45, that equals 2 under root 2 cos of a. We want tan a and tan b, right? This is a compound angle. We can expand this first of all. After expanding, we've got sine here, cos here, cos here. We can convert it to tan, right? Dividing by cos, that converts to tan, and we get tan a equals 3. Similarly, in the other equation, now we've got secant square. Now you need to remember secant square and tan square, they are connected to each other. So secant square can be converted to 1 plus tan square like this. And then you solve this equation, it's a quadratic equation, and that gives you tan b equal to 3 over 2. Once you have tan a and tan b, you just input them in that identity, tan a minus tan b divided by 1 plus tan a tan b, and that will give you the exact value for that. So sometimes you can have something like this as well, in which you have to solve simultaneous equations, okay, to find the exact value of something here. Now, some examples from some recent papers. You have to express this thing in the form r sine of x plus alpha. Now, how would that be done? This is not the standard form, right? We want to convert it to sine. The first term is indeed sine, but the problem is this is sine x, this is cos of x plus pi over 4. This is some different angle. So before we can convert it to r sine of x plus alpha, we first need to simplify this thing, right? How do we do that? Using the compound angle identity for cos. Cos of a plus b is cos a cos b minus sine a sine b. We use that identity to expand this thing. And then we simplify this. Cos of pi over 4, we can evaluate this on the calculator, under root 2 over 2. This is also under root 2 over 2. Then you simplify this further and you end up getting sine x plus 2 cos x after simplification. Once you've got this, then after that, now you can say it is the standard form. You want to convert it to r sine of x plus alpha. Now you can use the formulas. R is equal to square root of a squared plus b squared. Tan alpha is b over a. And then that gives you that form that you wanted there. Okay. Then in the next part, they're saying, hence solve this equation. Now, in the first part, what we've done is, in the first part, we have written this expression in this form, under root 5 into sine of x plus 1.107. Okay, that's what we've done in the first part. Now, is that related to that somehow? On the left side, you can have a look at this. Is it connected? In place of x, we've got half theta. In place of x, we've got half theta. That's one thing that is changing. But also, the numbers that you had there were 3 and 2 under root 2. This is 6 and 4 under root 2. So it's also being multiplied by 2. So one thing is that x is being replaced with half theta, and the whole expression is being multiplied by 2. So if this is equivalent to under root 5 into sine of x plus 1.107, then 2 times this should be equal to 2 times that. We can multiply both of them by 2. This is 2 times that, right? So we could say this left-hand side, therefore, this can be written as 2 under root 5 into sine of that. And then we also replace x with half theta here, right? Because in place of x, we've got half theta. So that's the tricky part here. Once you've done that, the rest is standard process as before, although that's pretty long. What do we do after this? You've got this angle, you use a substitution with this. You say let a equals half theta plus 1.107. Then you adjust the interval. Theta is given to be between minus 4 pi and plus 4 pi. You adjust the interval for that. If a is equal to this, we input theta equal to minus 4 pi here and theta equal to 4 pi here. That gives us the corresponding values for a. Their turn out to be this. A is supposed to be within this interval. And then 2 under root 5 into sine of a, that equals 3. Sine of a equals 3 over 2 under root 5. We find the basic angle. And then we find the values of a from that. A is supposed to be within this interval. Sine is positive, that's the first quadrant or the second quadrant. Now inside this interval, we actually end up getting 4 possible values of a. First quadrant, that's this. Then second quadrant, that's this. But then the interval is going beyond 2 pi. So if we complete one full circle, we can come back here again. That's this angle, another possible value of a. And then the interval is going in the negative direction as well. So we can go like this as well. And that gives you another possible angle. That is this one. Right? So you're getting 4 possible values of a. Then you put that substitution back and you get the corresponding values of theta from that. I'll leave this here for a few seconds. Have a look at this again later on. Slow down a little and you would understand this. Okay. You can go through this again in your own time. Okay, let's move on. This is another question from a recent paper. They are saying by first expanding this thing or otherwise show that cos raised to power 6 plus sine raised to power 6, that is equal to this. Now, how do we do that? They have given you a hint that you have to expand this thing, cos square x plus sine square x whole cube. Now, how do you do this expansion? This is cube, right? You can use binomial expansion, or you could do it like this, a plus b into a plus b whole squared. You could say a plus b into a plus b whole squared. You could do it like that as well. Although it's simpler to use the binomial expansion. Power 3, that becomes 3c1 here, which is 3, 3c1, 3c2 here, which is also 3, and you end up getting this expression. It helps to remember this as well. It's helpful in complex numbers later on as well. Sometimes they ask you to evaluate cubes like this. I would recommend that you remember this identity or just use binomial. A plus b whole cube is a cube plus 3a squared b plus 3ab squared plus b cube. We use that to expand this thing. So cos square x plus sine square x cube, that expands to this. Okay, that's what they hinted towards. They said by first expanding this thing, okay, we've done that expansion. Then we simplify this. Now, what do we want at the end? We want cos raised to power 6x plus sine raised to power 6x equals 1 minus this. Okay, so when we expand this, we are getting this thing after simplification. Now, on the left side, we've got cos square x plus sine square x whole cube. Since we don't want that in the final result anywhere, we can say cos square plus sine square is 1. Just replace that with 1. So that gives us 1 on the left side. We want this 1 here, right? And then on the right side, now we have this. We want to keep this thing on one side, take everything else to the other side. This is the other thing that we're left with. So now think of these two terms. How can you simplify this? You can take 3 cos square x sine square x common from this. That leaves you with cos square x plus sine square x inside, which becomes 1. And then you have 3 cos square x into sine square x. You have to find a way to convert it to this form. How do you do that? This is a double angle. You have the double angle identity for sine. Sine 2 is 2 sine a cos a. If you square that, because you want to square here, you can square that. Squaring that gives you sine square 2a equals 4 sine square a into cos square a. And then you could say this is cos square sine square. If you want to replace it with the double angle, you can divide by 4 on the other side. this 4 can go to the other side and you get sine square a cos square a that is identical to this. And now you can replace cos square into sine square with 1 over 4 sine square 2x, rearrange that, and you get that form that was required. A lot of thinking for 4 marks. Sometimes it can get as complicated as this. Again, I'm leaving this here. You can have a look at this a bit slowly later on as well. This is another example. We have to solve this equation tan cube plus 2 tan 2x minus tan x equals 0. We have to show that it can be expressed in this way. Now, the first part is not that difficult because we just have to apply the double angle identity for tan here. This is tan of 2x, right? So apply the double angle identity for that. Simplify that. You're getting tan raised to power 5x here. You can take tan common outside. If you take tan common outside, you get tan x equal to 0 from that. The question tells you that tan x is not equal to 0. So that does not give you anything. The other equation, when simplified, that gives you that form that they wanted. So the first part is fairly straightforward. But then they say, hence solve this equation tan cube 2 theta plus 2 tan 4 theta minus tan 2 theta is equal to 0. Now, in the first part, what we did was we started from an equation like this, tan cube x plus 2 tan 2x minus tan x equal to 0, and we showed that that could be written in this form. Okay, now compare with that. In place of x, we've got 2 theta, and that's it. That's the only thing that has changed, right? In place of x, we've got 2 theta. So in this form as well, what we do is we replace x with 2 theta, and then we solve it further. Now it's a quartic equation, right? Power 4 equation. We can use substitution to make it a quadratic. It's a disguised quadratic, right? Power 4, power 2. We could treat it as a disguised quadratic, hidden quadratic equation, solve it as that quadratic at the end. You put that substitution back, tan square 2 theta is equal to that or equal to this. Tan square cannot be negative, right? A square number cannot be negative. So we don't get anything from this. For the other one, we take square root. We get plus minus square root of 3. Do not forget plus minus whenever you take square root. For any even root, sometimes you have to take 4th root, 6th root, square root, all of these, they will always have plus minus with them. Any even root will have plus minus. So then we use a substitution. This is 2 theta. We could, since theta is given to be between 0 to pi, if a is equal to 2 theta, then a is between 0 to 2 pi. You solve this equation in terms of a. Tan could either be positive or negative. That means all the 4 quadrants are possible, right? Plus minus, that means all the 4 quadrants are possible. You write down the values of a in all 4 quadrants. You get this value, this value, this value, this value. Put that substitution back. A is equal to 2 theta. And that gives you the corresponding values of theta. Sometimes the trigonometry questions, they end up becoming quite long like this. It was only a 3-mark question. A lot of work for that, right? Yeah, okay. Let's move on. No, that's it. That's all that we had to do today on trigonometry. Have a look at these examples that I showed you at the end. These are some of the more complicated questions from recent papers. But that's it for today. I hope this was helpful. We end this here. If you have any quick questions, you can let me know.